Okay, Royals. For lesson 6.5, let's review our laws of logarithms by building them from the laws of powers. I'm not going to do the same proof that we did in the lesson or in class. Let's just develop some skills for reading this in the proper way. In grade 9, I ask my students to write this in English, and they shouldn't be saying when you multiply, you add it, or even when you multiply two powers, you add the exponents. There's three important features here. First, to identify that we are multiplying. Next, to identify that it is powers that we are multiplying. We're not multiplying bases. There's no b times b here, or there's a lot of b times b's, but there's definitely not just one b times b here. And we're not multiplying exponents. It's not m times n here. This is one power of b multiplied by another power of b. So we are multiplying powers. Those powers have the same base. To multiply powers with the same base. We don't just add the exponents. That would imply that b to the exponent m times b to the exponent n is m plus n, and that's not true. What we do is we keep the base. And then we add the exponents. And the nice thing about this rule, like most math rules, especially the ones that we've learned in our course, is that we could figure them out for ourselves. We don't need to memorize this. If I give you 2 to the exponent, I don't know, 7 times 2 to the exponent 6, I guess I could write it out as 1, 2, 3, 4, 5, 6, 7 factors of 2 multiplied by 1, 2, 3, 4, 5, 6 factors of 2. I'm not going to do 2 times 2 is 4 and then do 7 plus 6. I don't have repeated powers of 4. There are some powers of 4 in here, but I'm not seeing 13 of them. I'm seeing 13 repeated factors of 2. And I get that by keeping my base and adding my exponents. So the logarithmic version of this says, if I have, let's call it, I don't know. I don't want to use m and n because those are exponents up here. Let's call it like a and c. So first off, what are a and c? Well, a and c are inputs into a logarithm. And the only thing that I'm allowed to put inputs into logarithms are powers. Those two powers are being multiplied. And both of those powers are on the same base. So let's try this in English. To multiply, multiplication, two powers, a and c, there's two of them, and they're inputs into a logarithm, which means they have to be powers, with the same base. Well, there's only one base here. That base is b. What I'm going to do, let's just read forward a little bit. I'm going to be adding two exponents. The two exponents that I'm going to be adding are two logarithms, because logarithms are exponents. Here's me keeping my base. Notice how the base is still the same, and I am adding two exponents. Adding these things, logarithms, also known as exponents. So while the rule looks different, it is the exact same thing as your grade 9 power law. This is written in exponential form. This is written in logarithmic form. Okay. Same thing here. Let's try this a little faster. B to the exponent m divided by b to the exponent n is b to the exponent m minus n. Normally we would need to say my base can't equal 0. We don't need to worry about that with logarithms because we'll only be looking at bases that are greater than 0. This says to divide two powers with the same base. Right? I am not dividing bases. I'm not dividing exponents. The things that I am dividing are called powers. Notice that I do not divide the bases. Not really. I don't just cancel them out or cross them out and I'm left with 1 to the exponent m minus n. If that was the case, then every answer would be 1. No, what we do is we keep the base and subtract the exponents. Right. if I were to have 2 to the exponent 400 divided by 2 to the exponent 396, a question that most calculators can't handle, by the way, because the number is too big, there is some division of 2's. 396 of those factors of 2 would be divided out, and I would be left with a surplus of 4 factors of 2. Notice I'm not doing 2 divided by 2 equals 1. I'm not dividing my bases. I'm keeping the base. In logarithmic form, log base b of a quotient of powers. These are powers because they're inputs in a logarithm. They're being divided because there's a division bar there. To divide 2 powers with the same base, you keep your base. You take your 2 exponents. Log base b of a is one of the exponents. Log base b of c is the other exponent. And you subtract them. To divide 2 powers with the same base, you keep your base and subtract your exponents. And by far the most powerful and most useful property, the power of a power. Right. Identifying this as a power of a power involves saying that there's more than one base. Maybe we can do it with the exponents first. I'm seeing at least 2 exponents. If your exponent is m, then your base is b, which means that your power is b to the exponent m. This is called a power of b. Specifically the mth power of b, because it is an exponent written on a base of b. This right here is a power of 2. That's a power of 2. 16 is a power of 2. Okay? But then the other exponent that I see, if I look at the exponent of n, then the base on that exponent is going to be b to the exponent m. And that means that my power here is going to be b to the exponent m to the exponent n. Now, that means that this right here can be read as the nth power of b to the exponent m, which is itself a power. So that means that this right here can be referred to as a power of a power. Okay? It's the nth power of the mth power of b. This is probably why people started saying b to the power m. And that's just, it's not equivalent, right? If I say, oh, the 4th power of 2 is 16, that doesn't mean that 4 is the power. When I read it in English, when I say the 4th power of 2 is 16, the power is 16, not 4. 4 is the exponent. The word 4th doesn't mean that, like, 4 is the power. Just like if I say, I'm the 2nd son in my family, that doesn't mean that I am 2. It's a label of my position. Okay, our rule in grade 9 was to simplify the power of a power. We keep our base and multiply our exponents. To simplify the power of a power. Notice we don't need to say with the same base, because there are actually different bases here. You keep your most fundamental base. Usually when we say keep the base, students understand what we mean. And multiply. There's a cat on the table. Heads up, in case you're allergic to videos of cats. Keep the base and multiply the exponents. Right? You're not multiplying the powers. You're definitely not multiplying bases. The things that you are multiplying are exponents. So here we go. If we have log base b of, let's call it a to the exponent c. Now, I know that this is a power because it has a base to an exponent. I also know that it is a power because it is an input in a logarithm. And that's why there is a power of a power here. That thing under my finger is a power, but it is itself a power. What I'm going to do is I'm going to keep my base, log base b, and I'm going to multiply the 2 exponents that I see here. The 2 exponents that I see, one of them is c, and the other exponent that I'll find is log base b of a. Now, this does not mean you can magically move exponents into coefficients like this. This is not log base b of a to the exponent c. That's not c times. That wouldn't make any sense. There are very few numbers where raising it to the exponent is the same as multiplying by that number. Okay. This right here is a power of an exponent. We don't want a power of an exponent. We want a power of a power. Reading it in English is probably your best approach. That'll avoid memorization. Let's just get one more practice question using these rules in reverse. Let's say write a times log base b of c minus log base b of d plus 1/2 log base b of e as a single logarithm. Logarithm. Right. All right, so I'm looking for opportunities to use properties. Here's a subtraction, but this right now is not a single logarithm. It's a product of a number with a logarithm. So I need to use that property first, kind of a reverse BEDMAS. Here are two exponents that are being multiplied. I know log base b of c is an exponent because it's a logarithm, and that's what logarithms are. I know that a then has to be an exponent because the only thing I could multiply exponents by are other exponents. I ask myself, when would I have multiplied exponents together? The answer is in grade 9. In grade 9, when would I have multiplied exponents together? When simplifying the power of a power. So a times log base b of c is log base b of c to the exponent a. Let's hang on to this guy for one line. Doesn't look like he's doing much there. I mean, you can put brackets around it, I suppose. And let's try this right here. 1/2 times log base b of e. We could write as log base b of e to the exponent 1/2, but we're usually prompted to use integer exponents. So I'll deal with you in a sec here. Before I do that, I see an opportunity here. I see a subtraction of two exponents. I know these are exponents because they're logarithms. I ask myself, when would I have subtracted exponents? The answer is when dividing two powers with the same base. And then I see plus, let's write e to the exponent 1/2 as the square root of e, like that. And then one last property, I see a sum of two exponents right here. When would I have added exponents on the same base? If my powers were being multiplied. So let's keep my base and multiply these powers. Why don't we keep a c to the exponent a, but in the numerator put a square root of e and have a d in the denominator. And this is one single logarithm. Turns out this expression is equivalent to log base b of c to the exponent a times the square root of e divided by d. Here, let's change the directions with integer exponents. Or maybe even natural. So we have a 2 there, that's a natural number. We have a positive 1 there, that's a natural number. Let's assume that a is a natural number. Good. You'll get some practice in your homework with this. Make sure you try it out.